Good day. I'm Dr. Ima Isiet, and I'm presenting our research with this following title, also supervised by my supervisor, Professor Sun. I'm currently a postdoctoral research fellow at the Department of Electrical and Electronics Engineering at University of Johannesburg, South Africa. So this is the layout of our presentation. And by way of introduction, the current energy system in South Africa is such that majority of the electricity currently being generated is through conventional sources which have high greenhouse gas emissions. Currently, about 47 megawatts is being generated from such sources, specifically in thermal stations, and meaning only about 5 megawatts is generated through renewable sources, which is currently quite low. So, one of the motivations for this research is to present preliminary results on the generation of alternative energy through solar panels and hybrid electric vehicles, which are gradually on the slow rise across South Africa. So smart grids have been seen as an effective approach, to leverage the advantages of both efficient utilization of renewable energy sources as well as, an intelligent scheduling of, these sources in order to properly augment, the consumption of end users in such a way that they both benefit as well as the distribution service operators. Now, this schematic shows just the salient points of the smart grid, and the aspect that we are dealing with is actually demand response, as we can see here. And it's what it involves is basically trying to balance the energy usage, especially in peak energy periods, in such a way that during those energy periods or during those peak periods, we try to utilize more of renewables than conventional sources, because at those times there is a higher demand, which will lead to higher rates for energy at those times. So within those times, we would like to augment energy usage from the consumer point of view with renewables. And like I said, specifically renewables from comprising electric vehicles and rooftop solar panels. So the scope of our research involves, like we said, using the demand response approach by designing a model using the multi-objective approach to kind of represent the energy usage for both rooftop solar panels and the hybrid electric vehicles during peak energy periods. And that basically is what demand response is all about. We just want to be able to maximize the benefits on both sides. That is from the distribution supplier side and also on the on the side of the end user, because once we can maximize the benefits to both, specifically reduced cost of energy for the end user and also reduce wear and tear on distribution equipment on the side of the distribution service operators, we can actually find a win-win situation using this demand response approach. So we'll be using an earlier proposed evolutionary algorithm to actually optimize the buy objective function that we are proposing in this research. So we are using a home energy management system model that has a number of appliances, that represents the appliances in a typical household across South Africa, and we actually have you designed this with up to 6 occupants in. So with these equations that we see here, you would be able to get more information about all the parameters that we used for the mathematical equations to design our bioobjective function within the paper, because this presentation cannot fully describe all these parameters. So I would advise that you please go through the paper to get more detailed information about the parameters. So this objective function we see here is kind of minimizing two things. First and foremost, the costs, the energy costs by the consumer, at a particular time t, and this time t represents typically an hour within a day. So this t is divided into 24, time slots, and then also minimizing the effect of the electric vehicle, battery, the long-term effect on the battery of the electric vehicle, as it operates in the vehicle to grid mode. What the vehicle to grid mode is basically a mode that allows the vehicle to give off excess this excess energy after the battery is fully charged back to the grid. And we know that if this coefficient, the battery usage coefficient is not optimized with time, that can affect the lifespan of the battery, and these are the constraints. Like I said, you get more information about each and every one of these parameters when you go through the paper. And this is the appliance schedule for the home energy management system that I mentioned a short while ago. These appliances are what are basically found in any average home in South Africa. These are the parameters for the dynamic non-dominated sorting genetic algorithm, which is, like I said, the algorithm that we proposed in our earlier work. You would find it among our references. And these are the parameter settings that we use for the evolutionary algorithm to be able to optimize the objective function that I just showed. Now, moving on to the results, we compared the performance of our own algorithm, evolutionary algorithm, with some existing well-performing algorithms, such as the dynamic non-dominated sorting genetic algorithm 2. Ours is the 3, and the multi-objective particle swarm optimization based on decomposition. So these are some of the best performing dynamic evolutionary algorithms currently available. So we actually compared the ability of our own algorithm to optimize our designed bioobjective function to the performance of these already existing algorithms. And the performance parameters that we actually use are the severity, the frequency of change. These are parameters that you use for dynamic optimization. And the results that we actually obtained showed that our own proposed algorithm actually outperformed the other two algorithms. That's why you see the results here. The figures that you see in bold are the better performing indices, and you can see that they are actually lower in terms of the mean inverted generational distance. That's a performance metric for dynamic optimizers. You can see that our own algorithm, evolutionary algorithm, proposed algorithm, that we came up with is actually does a better job at, minimizing the inverted generational distance between, prospective solution particles compared to the other two algorithms. And it's the same thing, you can also see a better performance also for the hypervolume, which is also another important metric for dynamic optimization. And looking at this graphic, we see that when we don't apply any demand response, using the approach that we talked about, through, utilizing the or renewable energy sources, that is from the battery, of the electric vehicle, and also the rooftop solar panels. That is basically when there's no demand response. You can see that, the energy cost, for the consumer, for, the consumers in this particular household being used as a case study is actually quite high, and you can see it's quite erratic, actually a lot of peaks there, which is not in the best interest of the final consumer. But using our proposed demand response, approach, you can see that this is a more flattened energy usage profile for the final consumer, which would actually benefit the consumer more and also benefit the the DSO as well. So these results actually show that the proposed approach actually has a lot of promise in actually flattening, the energy usage profile for the final consumer, and also maximizing, the equipment cost savings for the distribution service operator. So from the results obtained, we come to these particular conclusions: that the optimal scheduling of shiftable appliances while simultaneously utilizing renewable energy sources has immense benefits, like I've said, to the consumers, with respect to minimizing their daily energy cost, and the use of an adaptive mutation strategy and crossover, which is actually what we used, to implement our evolutionary algorithm, which gave it an edge over the other two well-performing, dynamic evolutionary algorithms, actually helps to improve, the results that we actually got from, the optimization. And of course, our further research will concentrate on adding more sources of alternative energy sources, such as the wind, and of course the standalone battery energy storage systems to the mix, to see, how we can even further improve, the benefits to both the final consumer and the distribution service operators. So thank you very much.